All right, in this video, we are going to focus on using the second derivative. The instructions here say to use the function, the first derivative and second derivative, to determine some things about the function. So in a previous video, we did this information here from the original function. We determined the domain. And then from the first derivative, we found critical values, and we made a sign chart for the first derivative, which then gave us information about where the original function is increasing and decreasing, and where we have a relative maximum and a relative minimum for the function. So we've already done that information in a previous video, and we're going to focus in this video on using the second derivative to get the additional information we can get from that. All right, so part of the reason I wrote this up here is just to emphasize that the process we're going to use is very much the same, but with the second derivative. But it tells us some different things about the graph. All right, so first of all, I need my first derivative so that I can find my second derivative. So the derivative of this, 6x minus 12. And then what we did last time was we found the critical values. We found those from taking the first derivative and setting that equal to 0, and also thinking about where that first derivative does not exist, and making sure that the values we got are actually in the domain of the function. So when we do that for the second derivative, there are different ways you can describe this, but I like to call them hypercritical values to connect back to this idea here. So the hypercritical values of the function are going to come from where the second derivative is equal to 0 and does not exist. So I'm going to look at where the second derivative is equal to 0. So you don't necessarily have to write this, but I'm just writing down what I'm going to do. Set that second derivative equal to 0. So I'm going to put in 0 for that second derivative and solve for x. So add 12 to both sides and divide through by 6. And that is in the domain of our function. So we always want to check that. That's why we always start with finding the domain. And then the other perhaps critical value, hypercritical value that I might have would be where the second derivative does not exist. So looking at this second derivative and thinking about, are there any values of x for which this function is undefined? There are not, so not on this problem. Okay, so I only have one hypercritical value, and then we're going to do the same thing that we did with the first derivative, but we're going to do that with the second derivative. So I'm going to make a sign chart. I'm going to make a number line. I'm going to put my values that I got from this work, so in this case there's only one, on that number line. And I'm going to check the sign of the second derivative. So similar work over here, but I was checking the sign of the first derivative. Here I'm going to check the sign of the second derivative. And this is a split point, so it splits that number line into two intervals, the region that is left of x equals 2 and the region that is right of x equals 2. So I'm just going to put in numbers on either side. I'm going to put those into the second derivative. Remember that we're checking the sign on that second derivative. So some number bigger than x equals 2, like 3, for example. So you can just, you don't care exactly what the number is, just the sign of the answer. So when I put in a number bigger than 2, like 3, I'll have 18 minus 12, which is a positive value. And then when I put in a number left of x equals 2, less than x equals 2, like x equals 1 or 0, any of those would work. So when I put that in, for example, when I put in x equals 0 is pretty easy because it'll make this term go away. I'll get negative 12, so negative. Okay, so remembering that the first derivative tells you where a function is increasing or decreasing, so that's uphill or downhill. But the second derivative tells you something different. The second derivative tells you about concavity. And so the way I like to write those, just to help students visualize what the concavity is we talked about in class using sort of happy faces and sad faces. So when the second derivative is negative, that tells us that the original function is concave down, or sometimes I make a little sad face like that, a negative second derivative, concave down. That's what a concave down function looks like. A positive second derivative tells us that the original function is concave up. So a little happy face, a positive second derivative and concave up. All right, so that is what it asked us to determine here, where the function is concave up, concave down, and has inflection points. So we've got really most of our work done here to be able to answer that. And then we're going to go ahead and sketch a graph kind of combining all of the information that we have here from the original function, first derivative, and second derivative. I'm going to go ahead and write down answers for the intervals where the function is concave up and concave down. So essentially they are these intervals of x values. So I would say here the function is concave down on this interval where we are left of x equals 2. So this would be for x values less than 2. You could write that as an inequality, x less than 2. In your homework, they'll want you to write that in an interval. So negative infinity to 2. And then we would say the function is concave up on this region here where x is bigger than 2. So 2 to infinity. All right, so the graph will be cupped downward when x is less than 2 and cupped upward like a happy face when x is greater than 2. Because we change concavity at x equals 2, that's what an inflection point is. It's a value where you change concavity. So I do have an inflection point. It's a point, inflection point. And so I'm going to write that as x comma y equals, just so that we're clear about that. So x coordinate would be 2. And then to find the y coordinate of a point, sometimes students get confused about where they're going to put in that 2. So just think about back in algebra. When you found x, y coordinates of points, that was before you knew anything about derivatives. So x, y coordinates of points, that's always plugging into the original function. And we did that also to find the y coordinates of these points as well in that last video. So I'm just going to go over here to my original function. I think we had made a chart for some of these values as well, but I'm going to just put in x equals 2, and then I'll get my y value here. So when I put in 2, I'll have 8 minus 6 times 2 squared, so minus 24 plus 1, so that is negative 15. And of course, you can use a calculator to help you with that if you have a calculator handy. All right, so I've answered the information that it asked me for here, where the function is concave up on this interval, where it's concave down on that interval, and then inflection points, there's one of them at 2, negative 15. The other thing that it asked me to do is sketch a graph. And so, of course, if you have a graphing calculator available, you can use the graphing calculator to help you with that graph. There are some points here that are probably going to be off the screen for a normal viewing window on a graphing calculator. But the other thing that you should be able to do is that if you are given information about a function, like that it is increasing and decreasing on some intervals and has a maximum and minimum point, concave up and concave down on some intervals, and has an inflection point, that you could actually just sketch the graph from the information without necessarily even having the original function to put into your graphing calculator. So I'm going to sketch this graph. Instead of putting the original function into my graphing calculator, I'm going to use this information from the first and second derivative to sketch a graph, and then maybe use a graphing calculator to verify that. Okay, so I have 3 important points that I won't want to plot. So I will want to make sure that I set up my axes so that I can fit those on the graph. So I need a lot of negative values on my y-axis here. I need to be able to go down to negative 31. So I'm actually going to scale this y-axis, maybe not by 1s because that's a lot. Maybe I'll scale by 2s. So negative 2, negative 4, negative 6, negative 8, negative 10. 12, 14, 16, 18, 20, 22, 24, 26, 28, 30. Okay, so negative 31 would be just a little bit past that. I'll go ahead and put one more mark there. And then I'll need positive direction on the y-axis too. My highest point on the graph that I'm going to show here is at 0, 1. So I just need to go a little bit in the positive y direction. My important points on the graph here are at x equals 0, 2, and 4. So I'm going to scale my x-axis a little differently than I scaled my y-axis so that I can kind of see everything, whether I do that on the calculator or just by hand so I can see everything and it's not all scrunched up. I'm going to scale my x-axis by 1 since I'm just going by, these numbers are all fairly close to 0. So if you're using some sort of scale that is different than just every mark is 1, you just want to label that so that somebody looking at your graph would be able to notice that. All right, I have 3 important points to go ahead and put on the graph, so I'm going to go ahead and plot those. 0, 1, right there, and that should be a maximum That's a high point on the graph. So that's going to be a peak on the graph. I have a minimum at 4, -31. I'm going to go ahead and write the coordinates of the point, but don't have to do that necessarily. And that's a minimum, so that should be a low point on the graph, a valley. And then I have an inflection point at 2, -15. That would be about right there. And that's not a peak or valley, but that's a place where it changes from sad face to happy face type of graph. Okay, so I want to put these things together so I know that the graph is going to be increasing when I am left of this point at 0, 1, and then decreasing on the other side. So the graph is going to be going uphill and then downhill. I also know the way it's bending as it goes up and down. It's not going to be straight lines. It's going to be cupped. That's the concavity. So I know that it's going to be like a sad face on that region. So when I am left of x equals 2, it's going to be increasing and then decreasing, but bent like a sad face. Okay, so instead of drawing those two things separately, I looked here and I looked here, and then I drew what was happening in that region. And again, I'm going to put this into my calculator and make sure that what I see on my calculator agrees with what I thought. But there are problems that you're going to be asked to do where you won't be given the original function. You'll just be given this kind of information and asked to sketch the picture from that as well. So you want to practice when you do have a calculator available. All right, and then when I am right of x equals 2, the function is going to be concave up or cupped like a happy face. And I know that the graph is going to go down, decreasing until it reaches this point at 4, -31, and then is going to be increasing, going up. So happy face in this region, down, and then up. Other things that you might remember from algebra, high school algebra or college algebra, wherever you took that algebra, is that because this is a degree 3 polynomial, you know something about the end behavior of that polynomial. It's a degree 3 polynomial with a lead coefficient that's positive. So you know the end behavior should be up. You know that it should pass through the x-axis at most 3 times because it's a degree 3 polynomial. So if you remember those things, that's fine. But the main thing that I want you to remember and be able to do is the stuff that's new, the calculus stuff. So the stuff about where the function's increasing and decreasing, so uphill, downhill, uphill, and then the concavity, sad face, happy face. All right, and then you should get out a calculator and graph it and make sure that it agrees with this. You'll want to make sure you set up your window so you can see these points on the graph. And remember that on a graphing calculator, sometimes it makes things look a little jagged just because of the screen resolution. The actual graph is not jagged. If it were jagged, I would have places where the derivative does not exist, but I didn't have any of those. So the calculus here tells you that it's a smooth function everywhere. All right, we'll look at another function in another video that has some slightly different behavior, but same idea.